Light doesn't move. You see that light up there, that bulb? It hits your eye, and you say, the light came from the bulb to my eye. It traveled. Now in this room, that trip is very fast. You don't notice the time it took, but you know it took some time. If that bulb with the sun, we all know the number, right? 8 minutes, roughly 500 seconds. So we are very comfortable with this idea, but I'm going to tell you something crazy. And I mean really crazy. Because it turns out that nature, she's a funny thing. She doesn't care what you think is sensible. She doesn't care about your common sense. Common sense is just a bundle of prejudices you acquired before you were 18. From the point of view of that photon, that little packet of light energy, it didn't leave, it didn't travel, and it didn't arrive. If you could ask the photon, how much time passed for you? How long did it take to get from the sun to the earth? The photon would not say 8 minutes. The photon would say 0. And how far did you travel, you ask? 93 million miles? The photon says, no, 0. To the light itself, the emission at the sun and the absorption in your eye happened at the exact same instant and at the exact same place. You see, we are going to talk about why, in a very deep four-dimensional geometric sense, light does not move. It implies that the universe is not a thing that changes and flows, but a block where everything is already written. Light just is. It is the glue that binds the geometry together. Now, how can I say such a ridiculous thing? Light doesn't move. You saw it move. You switch on a flashlight, the beam shoots out. We measure the speed c, 299,792,458 meters per second. We have a number for it. How can something with a speed not move? Well, to understand the cheat, the trick nature is playing on us, we have to look at this idea of speed. Let's go back to Galileo, good old common sense. Suppose I am standing on the ground and I throw a baseball. I have a good arm. I throw it at 100 miles an hour. You measure the speed of the ball, you get 100. Simple. Now, suppose I run forward at 10 miles an hour. And while I am running, I throw the ball forward. What happened? Well, it's additive. My speed plus the ball's speed, 100 plus 10. The ball goes 110 miles an hour relative to you standing on the ground. This is how the world works. Bullets, baseballs, trains. It's comforting. Now take a sound. I run and I shout. Does the sound go faster? No. The sound is a wave in the air. The air doesn't care that I'm running. The sound leaves my mouth and travels at the speed of sound, roughly 760 miles an hour relative to the air. If I run fast enough, I might catch up to my own sound. But the speed of the wave through the medium is fixed by the air pressure and temperature. However, relative to me, the speed changes. If I run towards the sound, it comes at me faster. Now, into light. For a long time, we thought light must be like sound. We thought there was an ether, a background air for the universe. If we moved through it, the light should look faster or slower. But then these two fellows, Michelson and Morley, and later a young man named Einstein, found out something distinct, something that violates the baseball rule. If I am in a rocket ship and I am going fast, I mean really fast, half the speed of light, and I turn on a flashlight and shoot a beam forward, and you are standing on a planet watching me fly by. Common sense says speed of light plus speed of rocket equals sign superfast light, right? Plus V. No. You measure the beam from my headlight, you get C. I measure the beam from my headlight. I get C. A guy flying in the opposite direction measures the beam. He gets C. It doesn't matter how fast you run. It doesn't matter how fast the source moves. It doesn't matter if you're running towards the light or away from it. The speed of light is always the same number. Huh? Now think about that. That is a miracle. That is a mystery. Why is nature conspiring to keep this number fixed? If I run at the baseball hits me harder and faster. If I run it, the light beam, it hits me at the exact same speed as if I was standing still. This tells us something profound. It tells us that c, this number we call the speed of light, isn't really the speed of stuff. It's not like the speed of a bullet. If it were just the speed of a particle, I could catch it. I could add to it. The fact that it is invariant, that nobody can agree on the distance the light traveled, that nobody can agree on the time it took, but we all agree on the speed, means that c is not a velocity in the traditional sense. It is a conversion factor. See this is a conversion factor, length to length. But c is the conversion factor between space and time. We used to think space was one thing, a box, and time was another thing, a ticking clock on the wall of the box. But Einstein showed us that they are part of the same material, the same fabric, and to measure them, we need a ruler that works for both. C is that ruler. It tells you how many meters of space are equivalent to 1 second of time. It's a lot of meters, by the way, 300 million of them. So we have to stop thinking of light as a thing moving through a background. We have to start thinking of it as a feature of the background itself. Now here's where the modern picture gets even more beautiful. It's not just light. We used to think gravity was instantaneous. Isaac Newton thought so. If the sun disappeared, Earth would fly off orbit instantly. But we know now, and we've measured it with these big machines, LIGO, these gravitational wave detectors, that gravity travels at CR2. If the sun vanished, we would orbit nothing for 8 minutes. We would see the light for 8 minutes. Then, at the exact same moment the sky goes dark, the Earth flies off into the void. Why do gravity and light, completely different things, travel at the same speed? Because c is the speed limit of causality. It is the speed at which the universe updates its own geometry. It's the refresh rate of reality. So if nothing can go faster than this and light goes exactly at this speed, what happens to the experience of the light itself? This is where we have to leave our common sense at the door. We have to look at the world from the perspective of the photon. And when we do, we find that for the photon, the universe collapses. The distance between the sun and the earth shrinks. How much does it shrink? Well, let's look at the math. We're going to look at the formula that destroys space and stops time. And when we are done with it, you will see why I say that light doesn't move, it just connects. So we have the speed limit, this c, and we've established that it's not a normal speed. It's a law of the universe. Now, I want to take you on a trip. I want to do an experiment that a young man named Albert Einstein did in his head when he was 16 years old. A teenager, can you imagine? Most teenagers are thinking about girls, or maybe today they're thinking about, I don't know, rock and roll. But Einstein was thinking about riding a beam of light. He asked himself a question. If I run fast enough, if I catch up to the light beam, what would I see? If light is a wave, like a wave in the ocean, and you surf right alongside the crest, the wave looks static relative to you. It's frozen, a frozen mountain of electromagnetic field. But Maxwell's equations, the laws of electricity, say you can't have a static light wave. The math falls apart. The wave must move at c. So Einstein was in a pickle. He had a paradox. To solve it, we have to build a rocket. Let's suppose you have a very good rocket, a Caltech budget rocket, and you take off in the Feynman and you accelerate, you push the pedal down until you're going 90% the speed of light, 0.9 c. Now you're sitting in the cockpit. You look at your watch, tick tock, it looks fine. You check your pulse, thump, thump, normal. You drink a cup of coffee, it pours normally. Inside the rocket, everything is perfectly ordinary. This is the principle of relativity. You cannot feel constant velocity. But I am standing here on Earth, and I have a very powerful telescope, and I am watching you through the window of your rocket as you zoom by at 90% the speed of light. What do I see? I don't see you drinking coffee normally. I see you moving like molasses. I see you lift the cup, and it takes forever to reach your lips. I look at your watch, and the second hand is dragging itself around the dial. Peak. Took. To me, your time has slowed down. Now, why? Is it a mechanical failure? Did the high speed gum up the gears of your watch? No, it's not the mechanism. It is time itself. To understand why, you have to think about a light clock. Imagine a clock that works by bouncing a photon between two mirrors. Up, down, one tick. If you're moving sideways, that photon has to travel diagonally to catch up with the mirrors. Diagonal is a longer path than straight up and down. But remember, the speed of light is constant. It cannot speed up to cover that extra distance. So if the speed is the same, but the distance is longer, the time must be longer. We call this time dilation, and we can calculate it precisely. Nature is very strict about her accounting. She uses a factor we call gamma. Now look at this piece. Don't be scared of it. It's just a fraction. Look at the bottom, 1 minus v squared over c squared. If you're standing still, v is 0. So it's 1 over 1. That's 1. Time passes at a rate of 1 second per second. Boring. But watch what happens as you pick up speed. As v gets closer to c, this fraction v squared gets closer to 1. And 1 minus something close to 1 is something very small. And the square root of something very small is still very small. And 1 divided by something very tiny is big. At 90% light speed, the factor is about 2.3. Your time runs twice as slow as mine. At 99% light speed, the factor is 7. You live 1 minute. I wait 7 minutes. At 99.999% light speed, the factor is hundreds. You could fly to the nearest star and back in what feels like a weekend, but you'd come back and all your friends would be dead of old age. But now, let's push it. Let's go to the limit. We are talking about light. Light doesn't go 99%. Light goes at 0. V equals c. Look at the equation. C squared divided by c squared is 1 for 1 minus 1 equals 0. The square root of 0 is 0. 1 divided by 0, poof, infinity. And the math blows up. What does it mean? It means that if you could actually travel at the speed of light, the time dilation factor becomes infinite. Time doesn't just slow down a lot, it stops. Absolute stillness. Now think about the photon. Let's take a photon leaving a quasar. A quasar is a very bright, very old galaxy core. Let's say it is 10 billion light years away. If we look through the telescope at Palomar Mountain, we see a little blip of light. We say, oh, that light left the quasar 10 billion years ago. While that light was traveling, the Earth was formed. Dinosaurs appeared. Dinosaurs died. Humans evolved. Built the telescope. That is our story. But what is the photon story? If you could interview that, the photon, Mr. Photon, you've been traveling for 10 billion years. You must be tired. The photon says, what do you mean I just left? But the trip took 10 billion years. No, says the photon, my watch didn't tick, not even once. I was emitted from the quasar and bang, I hit your detector instantaneously. For the light, there is no passage of time. The birth of the photon and the death of the photon are simultaneous events. It is born and it dies in the same moment. But it gets worse, or better, depending on how you like your physics. Relativity isn't just about time. Space and time are two sides of the same coin, right? If time stretches, space must squish. We'd call it length contraction. The formula is just the opposite. And if you move fast, the universe shrinks in the direction you are going. If you go at 90% the speed of light towards that quasar, the distance isn't 10 billion light years anymore, it shrinks. But what happens at C? Plug in V equals C, you get 0, L equals 0. Do you understand what that means? To us, the quasar is unfathomably far away. The universe is a vast, empty void. But to the photon, The distance from the quasar to Earth is zero. There is no space. And the universe in the direction of motion has collapsed completely to a flat sheet. So let's sum up the investigation. We asked, does light move? Well, what is motion? Motion is traveling a certain distance over a certain amount of time. Speed equals distance over time, but from the perspective of the light, time elapsed equals zero, distance traveled equals zero. If you travel zero distance in zero time, did you move? No. You didn't go anywhere. This is the cheat. This is the secret. Light doesn't travel through space. Light connects 2 points in space-time that for the light itself are touching. The quasar and your eye touch, the sun and the leaf touch. To the photon, the universe is not a place of travel, it is a place of instant connection. The separation, the distance, the weight, that is all our illusion, created because we are heavy, massive creatures who are stuck crawling through time at a slow pace. We are the ones moving. We are the ones waiting. The light is just the geometry of the universe checking in with itself. Now, this implies something very strange about the structure of reality. If the photon is already at the destination the moment it leaves the source, does that mean the future is already written? Does it mean the universe is a solid block? We're going to have to slice up this loaf of bread we call space-time to find out. All right, we've established something very strange. We said that for the light, time stops and distance shrinks to zero, but that sounds like a magic trick, doesn't it? It sounds like wordplay. To really understand it, to see why nature demands this, we have to draw a map, but not a map of California. We need a map of the universe. Now, pay attention. This is a map of existence. On this horizontal line, I'm going to put space, that's east and west, that's Pasadena to New York. And on this vertical line, I'm going to put time, that's yesterday to tomorrow. Now, we usually think of the world as a stage, as the stage is space, and the actors move around on the stage while the clock ticks. We think of time as something that flows, something that washes over us. But Einstein and a mathematician named Minkowski, who was actually Einstein's teacher, they said, no, that's wrong. The universe isn't a stage that changes. The universe is a block. It is a four-dimensional loaf of bread. Everything that has ever happened and everything that ever will happen is already inside the loaf. You are a long worm wiggling through this loaf. Your baby self is at one end of the worm, and your old man self is at the other end. And what we call now, this moment right here, is just us taking a slice through the loaf. But here's the catch. If I am moving, I slice the loaf at a different angle than you. My now is different from your now. This is the relativity of simultaneity. Now let's put light on this map. Since we are measuring distance in light years and time in years, light travels 1 unit of space in 1 unit of time, 1 to 1. The ratio is 1. So light is aligned at 45 degrees, but we call this the light cone. Inside the cone is your future. Outside the cone is elsewhere, places you can't reach, places you can't talk to. But the edge, the skin of the cone, that is where light lives. Now here is the deep part, the part that explains why light doesn't move. We need to measure distance on this map. In high school, you learned the Pythagorean theorem, right? If I go 3 miles east and 4 miles north, the distance is the hypotenuse. X squared plus y squared equals distance squared. 3 squared plus 4 squared equals 5 squared. Simple. Positive numbers plus positive number. But this is space-time. And space-time has a different rule. It has a different geometry. It's not Euclidean, it's Minkowski. And the rule for the distance between two events, what we call the interval, or ds squared, looks like this. Look at that sign, that minus sign. That is the most important minus sign in the history of human thought. It says that time and space work against each other. If you sit still in your chair, x equals 0. You're racing through time, it increases. You're accumulating distance in the time direction. If you move very fast through space, x is big, you steal from your time. But now, apply this to our friend, the photon. For a photon, we know the speed is c, and in our unit, c equals 1. So the distance it travels in space, x is exactly equal to the time that passes, t. If it goes 1 light year of distance, it takes 1 year of time, it's equals to t. To put that into the formula, interval equals t squared minus t squared. What is that? 0. The distance between the emission of a photon and its absorption measured in the four-dimensional geometry of the universe is 0. We call this a null geodesic. Geodesic means straight line, null means 0. Light travels on the lines of 0 distance. So when I said earlier that light doesn't go anywhere, I wasn't just making a philosophical joke. I was speaking geometric truth. In the four-dimensional block of the universe, the path of a photon has no length. The event star emits and the event I absorbs are effectively adjacent in space-time. Light is the stitching that pulls the fabric of the universe together so that two widely separated points touch. Now, I want to bring you up to date because physics didn't stop in 1955. You might have read in the papers about these big detectors, LIGO. In Washington and Louisiana, they found gravitational wave, two black holes colliding 1 billion light years away. They shook the universe, and that shake, that ripple in the loaf of bread, traveled to Earth. And how fast did it travel? They measured it. It arrived exactly when the light would have arrived. It traveled at c. Now, why? Gravity isn't light. Gravity is the shape of space. Why does the shape of space change at the speed of light? It's because we have the name wrong. We call c the speed of light. That's a historical accident. We saw the light first. But c isn't about light. c is the speed of causality. d is the stiffness of the space-time loaf. Imagine Jell-O. You have a big bowl of Jell-O. You tap one side. The wiggle travels through the Jell-O. How fast? Well, it depends on the stiffness of the Jell-O. Space-time is a stiff Jell-O, and c is the speed at which a wiggle can propagate. It is the speed at which the universe updates its own geometry. If the sun vanishes, the shape of gravity around it changes. That information cannot be everywhere at once. The universe has to update, pixel by pixel, point by point, and the maximum rate of that update is e. Light just happens to be a massless particle. It has no baggage. It has no inertia. It doesn't want to slow down. So when a photon is born, it looks at the speed limit sign and it says, I have no mass to hold me back. I am forced, compelled by the laws of geometry, to go at the maximum update speed. Gravity goes at c because it is the update. Light goes at c because it's a massless passenger on the update wave. So the photon rides the edge of the map. It rides the line where time and space cancel each other out. It surfs the update front of the universe. And that is why, to the photon, the universe is a singular, connected, instant experience. But no. How does the photon know where to go? If it doesn't experience time, how does it decide which path to take? Now we have to talk about the arrows. We have to talk about quantum mechanics, part 4. All right, we have looked at the stage, the space-time block. We know the geometry says the distance is 0, but now we have to look at the actor. We have to look at the light itself. And I'm going to have to ask you to do something difficult. I want you to forget about waves. In the 19th century, we thought light was a wave like water. But it turns out, if you look very closely, with very sensitive instruments, photomultipliers, you find that light arrives in raindrops. It arrives in lumps. Click, 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 click. Particles, photons. So the question is, if I have a source here and a detector here, and I shoot a photon, how does the photon know how to get from S to P? Does it go in a straight line? Does it solve the wave equation? I'm going to tell you how nature actually works, and it is so crazy, so preposterous, that you will not believe me. But you have to believe me because it agrees with experiment to 1 part in a billion. It is the most precise theory in the history of science. We call it quantum electrodynamics, or QED. To calculate the answer, we have to use a trick, a cheat. We use these little arrows. Technically, we call them probability amplitudes, but let's just call them arrows. Imagine a stopwatch with a single hand, and imagine that as a photon moves, it's if the hand on this stopwatch turns, it spins, tick, 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 tick. It spins very fast. The speed of the spin corresponds to the color of the light. Blue spins faster than red. Now, here's the rule. This is the entire rule of quantum mechanics in a nutshell. To find the probability of an event happening, you have to add up the arrows for all the possible ways that event could happen. So a photon leaves S and arrives at P. How did it get there? Common sense says it went in a straight line. But quantum mechanics says, no, that is just one way. The photon could have gone up to the ceiling, bounced off, and came down to P. It could have gone to the moon, did a loop-de-loop, and came back to P. It could have gone to the Andromeda galaxy and back. And here is the shocker. The photon takes all of these paths. It doesn't choose. It takes every single possible trajectory through space-time simultaneously. I know. It sounds like I've lost my mind. Professor Feynman, surely the light doesn't go to the moon to get from the bulb to my eye. But the math says it does. The math says we must sum the arrows for every path. So let's see what happens when we do that. Let's look at the crazy path first, the one that goes to the ceiling. That path is long. It takes a long time. While the photon is traveling that long path, the little stopwatch hand is spinning. Spin, 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 millions of times. When it arrives at P, the arrow is pointing in some direction, let's say 3 o'clock. Now let's look at a path slightly next to it, just a hair different. Because the path is crazy and long, a tiny change in the path makes a big difference in the time. So the stopwatch spins a little bit more or a little bit less. The arrow for this neighbor path points at 9 o'clock. Now, what happens when you add an arrow pointing right to an arrow pointing left? They cancel. They kill each other. Destructive interference. The arrow for the moon path points one way. The arrow for the path 1 inch next to the moon path points the opposite way. The vast majority of the universe, the crazy paths, the loops, the zigzags, they all wash out. Their contribution to the final answer is 0. But now, look at the straight line, the shortest path. In geometry, the straight line is unique. It is a minimum. If you have a path that is the shortest and you wiggle it just a little bit, the length doesn't change much. But that's calculus. At the bottom of the curve, the slope is 0, flat. So if I look at the straight line path, the stopwatch turns a certain amount. If I look at a path just a microscopic bit to the left, the length is almost exactly the same. So the time is almost exactly the same. So the stopwatch arrow points in almost exactly the same direction. They don't cancel. They reinforce. They pile up. The probability is the length of this final arrow squared. And the only place where you get a big arrow is right around the straight line. This is why light looks like it travels in a straight line. It's not because the photon chose the straight line. It's because the photon explored the entire universe, but the only place where the arrows didn't destroy each other was along the path of least time. We call this the principle of least action. Now, what does this have to do with our topic? Light does not move. Remember our four-dimensional map? We said the distance, the interval along the light path is 0. In advanced mechanics, we call the quantity we are minimizing the action. For light, the action is zero. Think about what that implies. The phase, the turning of the arrow, is stationary. It stops spinning relative to the path variation. This connects back to our no-time idea. If you are the photon and your internal clock doesn't tick because of relativity, then the arrow cannot turn. From the photon's point of view, the arrow is frozen. The emission arrow and the absorption arrow are the same arrow. So how does the connection happen? The quantum probability amplitude finds the path where the connection is stable. The light isn't a traveler fighting its way through the air. The light is a manifestation of a probability connection between 2 points in space-time, and that connection only becomes real, observable, where the geometry allows the phases to line up. This implies that the path of the beam is not a trajectory of a bullet. It is a resonance. It's like a guitar string. You pluck it, the whole string vibrates. You don't say the vibration move from one end to the other. The string just is. The path of light is a string connecting the start and the end, vibrating in the fourth dimension. The straight line is just the mode of vibration that survived. So we have a double whammy. Relativity says for the photon, the trip takes 0 seconds and covers 0 distance. Quantum mechanics says the photon is everywhere at once, but the only reality that emerges is the one along the path where the phase is stationary. The photon doesn't go. The photon is. It is a handshake. The electron in the sun shakes its hand, and the electron in your eye shakes back. And the photon is just the agreement, the contract, the exchange of momentum that happens across the zero-interval bridge between them. Now, this brings up a philosophical problem, a big one. If the photon smells all the paths, if it checks the moon and the ceiling before it decides to land in your eye, does that mean the photon knows the future? Does the photon know you are going to be there to catch it before it leaves a star? This is where things get really spooky. This brings us to the absorber theory, part 5. Now, I want to tell you a story. A long time ago, when I was a graduate student at Princeton, I got a phone call from my professor, John Wheeler. Johnny Wheeler was a crazy guy, a genius, but he had an imagination that was completely unconstrained by reality. He calls me up and says, "Feynman, I know why all electrons have the same charge and the same mass." I said, "Why?" "Hey," he says, "because they are all the same electron." He had this idea that there was just one electron in the universe, going forward and backward in time, weaving the whole tapestry of matter. Now, we laughed about that, but Wheeler had another idea during that time, a profound idea about light, and it relates directly to this problem of motion. We usually think of a light source like a star as a generous giver. It stands there in space and spews out energy. It radiates. It doesn't care if anyone is watching. It just pours light out into the void. And if you happen to be standing there with your eye, you catch a little bit of it. But Wheeler said, "Feynman, that's wrong. You can't emit light unless there is something there to absorb it." Think about that. It implies that the emission and the absorption are not two separate events. They're two ends of the same stick. If you are blind and you poke a stick out, you don't feel anything until the stick hits a wall. The pressure on your hand, the emission, and the resistance of the wall, the absorption, happens simultaneously. You can't have the pressure without the wall. So let's apply this to our photon that travels at the speed of light, which means for the photon, 0 time and 0 distance. If 0 time passes for the photon, then the moment it leaves the star and the moment it hits your eye are the same moment in its existence. So from the point of view of the electromagnetic field, the star and your eye are in a handshake, a direct contact. The star shakes the field and your eye shakes back instantly. Now, this leads to a very spooky philosophical conclusion. We call it the absorber theory. It suggests that the star creates the light because your eye is there to catch it 1,000,000 years later. I know. You're saying, but Professor, the star burned 1 million years ago. My eye wasn't born yet. But remember, the universe is a block. The future is already there in the geometry. So in the four-dimensional loaf of bread, the event star burns and the event you see it are linked by a thread of zero interval. The transaction is complete across the gap of history. We don't teach this in the freshman physics course. Why? Because it confuses people. It scares them. It suggests that the future, your eye, determines the past, the emission. It violates our human sense of cause and effect. But the math of quantum electrodynamics, the little arrows I showed you, it doesn't care about your sense of cause and effect. The math works both ways. The equations are symmetric. You can run the film backward or forward. To the light, there is no before and after. There is only the connection. Now, you might say, Feynman, this is just philosophy. This is old stuff. But it's not. This is actually where modern physics is going right now. You look at the journals today and you see words like non-locality and entanglement. You've heard of this, right? It's the Bell's theorem. You take two particles, you smash them together and send them to opposite sides of the galaxy. Quantum mechanics says they are still the same system. If you tickle one, the other one laughs instantly, faster than the speed of light. Oh, no, because nothing's traveled between them. People get very upset about this. Einstein got very upset about this. He called it spooky action at a distance. He said, God doesn't play dice. And he certainly doesn't play magic tricks where one thing affects another thing 1,000,000,000 miles away instantly. But think about what we learned today. What is distance? Distance is something we'd experience because we are made of heavy particles. We are made of fermions. We have mass. We are sluggish. We drag our feet through the space-time mud. For us, space is a barrier. It takes effort to cross it. But for the forces of nature, for the light, for the fields, distance is an illusion. The distance between the two entangled particles measured along the light cone is zero. They aren't far apart in the four-dimensional geometry. They are touching, just like the star and your eye are touching. So maybe non-locality isn't a mystery. Maybe it's just the universe telling us that locality, the idea that things are only here and not there, is the real illusion. Maybe the universe is much more connected than we think. And we think of the world as a bag of marbles, separate marble. But the light tells us the world is a spider web. If you touch one part of the web, the whole thing vibrates. And the vibration doesn't have to travel if the web is tight enough. The web is the connection. So the handshake, the light doesn't move. The light is the tension in the web between the past and the future. The light is the universe agreeing with itself. Now, does this mean you can send a telegram to your grandfather and kill him before you were born? No, because the probability amplitudes, the arrows, they rely on interference. If you try to change the past, you scramble the arrows, the probability goes to zero. Nature is very good at protecting her history. She doesn't let you cheat the logic, even if she lets you cheat the space. But it does mean that when you look up at the night sky, you're not just a passive observer. You're not just a bucket collecting old rain. By being there, by absorbing that photon, you are completing a transaction that started at the beginning of time. You are part of the circuit. You and the star are dancing, and the light is the music. So we have the geometry, relativity. We have the mechanism, quantum mechanics. And we have the meaning, the handshake. It all points to one thing: the beam is static. But what does that mean for us, for the way we live our lives? Let's wrap this up. Part 6. So, we've been here for an hour and a half. We've gone to the moon. We've chased rocket ships, and we've looked at the very fabric of reality. And we come back to the simple question we started with. The question a child might ask: does light move? And the answer, like everything in physics, depends entirely on who is asking. If you are the controller of the universe, if you are standing outside of time, looking at the whole block of space-time, the whole loaf of bread at once? Then the answer is no. You look at the map and you see a line connecting the star to the eye. It's a static line drawn on the paper. It doesn't wiggle, it doesn't flow, it just is. The history of the universe is a geometry, not a movie. If you are the photon, if you are the actor in the drama, the answer is no. Because for you, the clock never started. You were born in the fusion fire of the sun, and you died in the retina of a human. And those two events happened at the same instant. You are everywhere on your path at once. You span the gap like a bridge, not a traveler. But if you are these biology machines made of heavy atoms stuck in this slow, sticky mud called matter, then the answer is yes. Because we are trapped. We are forced to experience the universe one slice at a time. We are crawling through time. And because we are slow, the light seems to zip past us. The speed of light is really just a measure of our own slowness. It's a measure of how hard it is for us to update our reality compared to how fast the universe actually updates. You see, this is the thing I love about physics. We start with common sense. The things move, and we poke at it, we push it, and suddenly common sense falls apart. Nature is much more imaginative than we are. She's smarter than we are. We think moving is the only way to get from A to B. We think you have to buy a ticket and sit on the train. Nature says, no, that's the hard way. If you go fast enough, if you lose your mass, if you become pure energy, then A and B are the same place. We are just the slow pokes. We are watching the grand static tapestry of light through a tiny slit, and because we drag that slit across the picture, we think we are watching a motion picture. But the picture itself, the light, is timeless. So tonight, when you go home, I want you to walk outside. I want you to look up, find a star, maybe Sirius, maybe a planet like Jupiter, and look at it. Don't think, oh, that light traveled for 10 years to get to me. No. I want you to realize that, strictly speaking, geometrically speaking, you are touching it. Your eye and that star are touching. You are connected by a bridge where time does not exist. You are shaking hands with the universe across the void. The light doesn't move, it connects, and you are part of the connection. Thank you.